Okay, just to finish up part A there, I forgot to verify my solution using graphing technology was part of the question. So we figured out that we think the graph is increasing everywhere except we think at -3/2 there's a flat spot. So let's just head over to Desmos to check that. So here's, I've typed in the equation off to the side, and I can see that that's what's happening here. Less than -3/2 or -1.5, I'm increasing, and then when I get there, there's this little flat spot here. It kind of looks like a cubic, even though this is a power of 7 graph, and then after that, it continues to increase. All right, so moving on to part B, we're going to see what we can figure out about what this graph looks like. We know it's a rational function, so we know that there's some odd behaviors there that might pop up. And we're going to investigate some more unusual ones in calculus than we did in advanced functions. All right, so I know that my algorithm says to start by looking at the value of the derivative, but I'm going to remember that in another part of the algorithm, it tells me to remember or to check for where f at x does not exist. So I'm going to look for that in the original equation, where does the function not exist? And it's wherever the denominator does not equal 0. So here I can see that f at x does not exist when x is equal to 2, right? If I put a 2 in here for x, I get 2 minus 2 is 0, and 0 squared is 0. So x equals 2 is going to be an important value for me later on. I'm not going to forget about that. Now, taking the derivative of this guy, I have something with x's divided by something with x's. So I'm thinking about the quotient rule. All right, so I'm going to take the derivative of the top. The derivative of the top here is just 1. And I'm going to multiply it by the denominator. And then I'll subtract. This time I'm going to leave the numerator alone and take the derivative of the denominator. Don't forget, when I take the derivative of the denominator, I'm taking the power out front. The chain rule tells me to take the derivative of the outer function and then multiply by the derivative of the inner bracket. So the derivative of x minus 2 is just 1. And I'm going to put that all over the old denominator squared. Remember that when you square something that's already being squared, you're going to multiply the exponents. So 2 times 2 gives me a new exponent of 4. All right, now I know that I want to know when this derivative is equal to 0. It's going to help me find those maximum minimums. So I'm going to try to factor and simplify out this numerator. So let's just write this a little bit cleaner. I don't need that 1 coefficient. And over here, I'm just going to bring the coefficients to the front. So I've got 2 times 1, that's 2, and it was already negative. And then I've got the x times the bracket. Okay, so I still have some cleaning up to do in the numerator, but in the denominator, what I notice now is I have 0 equals 1 fraction. And as soon as I have 0 equals a fraction, I can bring the denominator up to the other side and multiply it by 0. And I end up with just the numerator is equal to 0. And you can skip this, instead of rewriting the numerator, you could start to simplify it at this point. Now what I notice is I've got 2 terms. The first term is a bracket being squared, and I'm subtracting 2 times x times that same bracket. So I'm going to use my factoring magic here, and I'm going to pull the common bracket out front. If you didn't do that, you would expand all of this and then collect like terms and then refactor it, and you're going to end up with the same answer as me in a couple more steps. So I'm bringing out a common factor of x minus 2 and then opening up a bracket and writing down the leftovers. So x minus 2 squared, if I divide by x minus 2, I'm left with 1 bracket. And you can put the round brackets here, but you don't need them. And then in the second term, when I divide out the x minus 2, I'm left with negative 2x. Oops. All right, so now we'll clean up that square bracket. I've got x minus 2x. I'll collect my like terms, and I get negative x minus 2. All right, so now when I go to solve this, I have 2 different solutions. I have x equals equals 2 from the first bracket, or in the second bracket, and you can write it out that I want the second bracket to equal 0 if that helps. I'm going to bring the negative x over to the other side and add it, and I get that x is negative 2. So I have two different solutions here. Now, I need to remember that for x equals 2, I need to go back to the derivative as soon as I moved it over to the other side. This is my last true f prime at x. This is not f prime at x, because at this point I lost the denominator, right? So keep track of that in your mind. I'm going back to f prime at x, and what I'm noticing is that it has a denominator of x minus 2, which tells me that f prime at x does not exist. And I'll actually write this as part of my solution. The red here I wouldn't usually write, but I'm just going to be thinking about it. F prime at x does not exist when x equals 2. And it's actually the same restriction that I got from my original function. Sometimes that'll happen, but just watch out to check for both. So what that tells me is this guy here that showed up as a solution, this is not actually a solution because it's not in the domain. So I have two values that I need to consider in my chart. I have x equals negative 2, and for my restrictions, I have x equals 2. So we're going to set up our table. Again, across the top, we're going to list out all those intervals. I'm always starting at negative infinity, and then I just start to list my values from smallest to biggest. So my smallest number is negative 2. So I'm going to look at that interval, and then I'll consider what's actually happening at negative 2. And then negative 2 to my next value is positive 2. Then we'll stop and consider what's actually happening at 2. And then our last interval is 2 up to positive infinity. So we had 2 values and 3 intervals. It should always be one more interval. All right, down the side here, first we're going to pick a test point. Then we're going to figure out, well, what is the sign of the derivative? And then finally, we're going to talk about what's the behavior of the actual graph that we're investigating. So in our first interval from negative infinity to negative 2, I'm going to pick some number that's smaller than negative 2. So again, I'm going to pick negative 10, but you could pick whatever number you want, negative 87, negative 3. And I'm going to go back up to my derivative. So again, I have to think about when did I start moving things across the equal sign? And it was at this point here, so I have to use the line above it. So I'm thinking about this one here, and I'm going to plug in, or you could even be thinking about this one here if you want. And I'm going to plug negative 10 into this and figure out what I get. So when I plug negative 10 into the numerator, I'm going to get negative 12 in this bracket being squared. That's 144. And then I'm going to subtract 2 times negative 10. So that's actually now positive 20 times negative 12 in the bracket. And so that's altogether going to come out as a positive number. Another way that you could check is you can use this down here is just a simplified version of the numerator. So I can use this and remember that this is just the numerator. And don't forget to come back to your denominator. So here it's a little bit easier. If I plug negative 10 in here, that's a negative number, times over here when I plug negative 10 in, it turns to positive, and this is a positive. So, oh, sorry, did I say, I think before I said it was positive. It's actually a negative answer. So I said, yeah, I've got a negative times a positive. So altogether, I've got a negative. And I'm going to divide by the denominator. When I think about this denominator here, the original denominator, it's to the power of 4. So no matter what number I put in here, if I raise something to the power of 4, it's always going to turn into a positive. So here it's a negative to the power of 4, but that's a positive. And overall, then I end up with a negative answer. All right, what does that tell me about the graph then? If the derivative is negative, that tells me the slope of the tangent is negative, and so the graph is decreasing or heading down. All right, at -2, what's happening? So we don't need a test point. We've already got our number -2. Remember, -2 we got because it made the derivative equal 0, so I don't need to investigate anything. And if the derivative is 0, the slope of the tangent is 0, or the original graph is flat. All right, next up we're going to pick a number between -2 and 2. I always like to pick 0 when I can. So again, investigating just the numerator here, I'm going to get 0 minus 2, so -2 times -2. That gives me a positive. And again, the denominator is always positive because I've got, here I'm going to have a negative number to the power of 4. And so overall I have a positive. And a positive derivative tells me the slope of the tangent is positive. So that tells me that my graph is increasing. And then at 2, again, I don't need to pick a test point. We came up with the value of 2 because the derivative actually does not exist there. Remember, we said it's actually not in the domain of the derivative or the original function. And so I'm going to remember that as well. The original function does not include the value of x equals 2. Then moving on to our last interval, picking any number bigger than 2. So you could pick 3, you could pick 1,000, whatever you like. I'm going to plug 10 into just my numerator, and I get a positive number times, over here I'm going to get a negative number. So a positive times a negative gives me a negative, and again my denominator is always positive. And overall that gives me a negative answer. Again, that tells me that the derivative is negative, which means the slope of the tangent is negative, which means that the graph is decreasing. And so then we'll draw our conclusion. Doesn't matter which order you go in. We have 2 decreasing intervals, one from -infinity to -2, and one from 2 to infinity. And remember, I do want to see the sentence. I want to see you connect these words at the bottom back to the intervals at the top. All right, the last part of this question asked me to take a look at what does it look like with graphing technology. How did we do here? So we're going to head over to Desmos. I had to rename it g at x because Desmos doesn't like when you call 2 functions f. Just reorganizing here. So we said that it's decreasing until you get to -2. So I'm going to just zoom into my y's here and see if we can figure out what's happening at -2. Yeah, and what we see here is it's decreasing, 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 and then all of a sudden it starts to come back up after -2. So that makes sense to us that there's a flat point at -2. And then I can see here that at +2 there's a vertical asymptote, so it makes sense that it doesn't exist on our function. So it was decreasing until -2 and then increasing, and then after the asymptote decreasing again, and it just continues to decrease to a horizontal asymptote. All right, so we're happy with that. And that's the end of our lesson today. Have fun with the homework.